Good morning and welcome to this webinar with Mr. Caicedo. He's going to hold the presentation about the nodal analysis. And Mr. Caicedo holds a bachelor degree in physics and computer science from Simón Bolívar University in Venezuela, as well as a master in petroleum engineer from the University of Texas at Austin. He has 27 years of experience as an specialist in artificial lift, well productivity, and software development applied to oil production. He also has worked as an instructor in oil production, where he has trained 700 plus engineers in the companies where he has worked. He has published around 30 technical papers, and Mr. Caicedo has worked as an specialist in artificial lifting in Venezuela, Kuwait, and the United Arab Emirates and the United States. And also, he was awarded with the SPE Middle East Production and Operation Award 215 for his technical contributions in artificial lift. Thank you, Sergio, for being here today. And please let us start with the presentation.
Okay, welcome everybody. This presentation promoted by UPC Global. Today topic is commonly misunderstood on unmentioned nodal analysis topics. So let's start with the topic, with the outline of this presentation. We are going to talk about the scope, the node locations, inflow definition, understanding inflow producer wells, reservoir performance or sentences, single phase and multi-phase inflow performance relationships, multi-phase flow, pressure drop correlations and outflow, multi-phase flow and well stability, node analysis for injection wells. So let's start with the scope. What does node analysis do? Well, node analysis does not determine where the water, the gas, or the sand comes from. Analysis does not determine the reservoir pressure and depletion time, does not determine the mechanism of source of damage in the porous media, does not determine the critical rates, sand production, water or gas coning. No analysis does not determine asphaltene flocculation pressure or paraffin solidification temperature. No analysis does not give solution to this problem, does not determine reserves, does not determine how long it takes to drain the reserves. No analysis does not allow to study dynamic process instability, intermittent gas well, for example. It's very important because I have seen many people trying to do things beyond the non-analysis capacity, and that is a lack of wasting time and getting results that do not represent anything. Okay? But let's see, what does non-analysis do? Well, non-analysis does allow determining the expected rate, if any, for a given condition of water percentage, GOR, etc. Non-analysis does allow determining the expected rate, if any, for a given reservoir pressure and or skin damage value. Knowing the critical rate, the non-analysis does allow determining the corresponding pressure through the production system for avoiding sand production or water gas coning. Knowing the flocculation pressure, the non-analysis does allow determining where the asphaltene flocculation or paraffin solidification takes place. Non-analysis does complement dynamic procedure for production, forecasting, and depletion, meaning that itself cannot do it, but can assist on our process like material balance, such as material balance, to do this task. Non-analysis does not allow evaluating performance for a given solution. Does not provide a solution, but given a solution, I can evaluate the performance of that solution. So let's talk about pressure distribution and node location. First thing we have to understand is that the boundary conditions, the fixed values, are the surface, the pressure at the surface, the pressure at the reservoir. Pressure at surface does not change. We are going to talk about this. Could be the separator pressure or the pump pressure for injectors. And reservoir pressure is not going to change in the short term. To see a change in the reservoir pressure, we need years. But wellhead pressure, flow line pressure, bottom-hole flowing pressure, tubing pressures, they can change in matter of hours. So these points, these blue highlighted items, they can change in matter of hours. Okay. So let's talk about the producer well with the node at the bottom hole. This is the most common and usually what people have as the idea of node analysis. This is just one possibility. Okay. So what is the idea of node analysis? The main idea is to define a node that could be any place, and I'm going to use at the bottom hole. The node location divides the problem in two big subsystems. The inflow or the upstream, anything that is located where the fluids come from into the node, and downstream are everything that where the fluids goes after the node. So when the node is at the bottom, the downstream is, or outflow is the tubing, and the upstream is the reservoir. It's very useful for the purpose of dividing the system in reservoir and production system. But inflow is, as I told you, is much more than that idea. What about a producer with the node at the wellhead? When we have the node at the wellhead, the inflow has everything from the reservoir, tubing, artificial lift, everything up to the wellhead. And the outflow is just the patterning system. And it's very useful for back allocation, for example. What about an injection well with a node at the bottom hole? We can use this, and then inflow, as we will see later, will be the pumping system at the surface and the tubing, and the outflow will be the reservoir when the node is at the bottom. So let's see one of the most common misunderstood points. Let's start with the linear inflow performance relationship with the node at bottom hole. The reservoir pressure is the intercept in the y-axis, and the productivity index is the slope, or the inverse of the slope, and they are independent properties. Many people think that if I have a high pressure, then I have a high productivity index, or if I have low pressure, I have a low productivity. You can have high pressure, high productivity index, high pressure, low productivity index. You can have low pressure, high productivity index, and low pressure, low productivity index. So they are independent. One of the reasons of this confusion is the equation that productivity index is equal to the reservoir pressure minus bottom hole flowing pressure divided by the rate. This is only valid for a single phase, but sometimes it's misinterpreted as that the productivity index depends on the reservoir pressure. No, this equation is the slope when I select 2 points. One point is rate 0 when the bottom hole reservoir pressure is 0, and the other point is a test rate with the downhole pressure test. Okay, so knowing that the reservoir pressure is the intercept and the productivity index is the slope, then we can do just for inspection answer the following equation for this case. For this case, both wells has the intersection point here with the same value. Regardless of the scale, I know that both wells have the same reservoir pressure, but well A has higher productivity index because it's more horizontal. Remember that is the productivity index is the inverse of the slope. So well A has higher productivity index. Absolute open flow, well A at 0 bottom hole pressure. And higher production, we cannot tell anything about production because we need the outflow course to see where is the operational point. So it could be well B if the bottom hole flowing pressure is low for well B, and well A has a high bottom hole flowing pressure. Without outflows, intersection point, I cannot tell anything about the current production. In this case, well B has higher productivity index because it's more horizontal, the inverse of low. Well, A has higher reservoir pressure because the intercept is higher. Well, B has higher absolute open flow, and we cannot tell anything about the production. In this case, we have higher productivity index is well A, higher reservoir pressure is also well A because the higher intercept. Higher absolute open flow is well A, and we cannot tell anything about production. In this case, higher productivity index is well B, higher reservoir pressure is well A, and both have the same absolute open flow. Production, again, we cannot tell anything about. So let's talk about uncertainties. That nobody talks about uncertainties in production. Uncertainties are very usually discussed in reservoir and exploration, reserve calculation, but not in production. And we need to do it. So when we compute the uncertainty for a production test, having the rate, the bottom hole pressure, and the pressure pressure, we have to know, be aware about the uncertainty of the having big uncertainty. What are the consequences? We are going to have poor flow rate prediction, risk of working on suitable conditions, inappropriate selection and sizing of equipment, especially when we are using artificial lift, pumps in particular, inappropriate actions on the well. Maybe you want to perform a stimulation and you don't need it. Well, reservoir real capacity not clear defined, so the potential of the well is not clear. Let's do it. Let's see this case when I am showing uncertainties in the reservoir pressure here in the horizontal. I have uncertainty in the bottom hole fluid pressure and uncertainties in the rate. As you can see, the possibilities range from this yellow inflow to this blue inflow. If I don't use the uncertainties, then I could think that I have a very low productivity index and I want to perform a stimulation. When in reality, what you have is a uncertainty problem. Okay? When you have low uncertainties, there's no big difference between these inflows, the yellow and the blue. What is more important are the predictions. With the condition A, it will say it will produce with the blue inflow, but cannot flow with the yellow inflow. With the condition B, the production with the inflow, yellow inflow is twice the production with the blue inflow. And with the condition C, you are taking most of the outflow of the potential if when you have the blue and you have in the middle of the potential when you have the yellow. So the predictions are the most important. When you have good small uncertainty predictions are almost the same for both. So it's important to measure to take into account uncertainties. When I using productivity index computed from Darcy law using petrophysical data, the big problems are the big values, the values with the biggest uncertainty are the permeability and the skin. There's no big uncertainty with the thickness, and you have to be aware of about the PVT properties, especially the DO and the viscosity. Meanwhile, the radius, drainage radius and the well radius is they are inside a logarithm, so the error in this is going to be small. Even if you have a big uncertainty in the radius, the logarithm is going to help. Note that in this equation we are not using in the test rate test and bottom hole test and the reservoir. So that tells you that this value does not depend on this. Okay, it depends on the permeability, especially skin, thickness, viscosity. Main. So let's talk about the skin a little bit. For this one, we need to think about the following example. The drainage radius 1,000 feet. Let's say that we have 1,000 psi pressure drop, the drawdown. The reservoir pressure is 1,050, and the bottom hole pressure 50. So the question to understand about the skin and everything, where do you expect to have the pressure drop about 500 psi? Most of the people say it in the at 500 feet above from the well. It is not, because this is logarithm. So 50% of the pressure drop is around 10 feet from the well. It's very close to the well. That means that when you have a damage created by a drilling fluid circulation loss, just in the nearby 10 feet is 50%. So it's very important to know what is the invasion and the loss circulation to have an idea of the consequence of this. So the skin is used to quantify the damage. But what is exactly the skin? The skin is a dimensionless pressure drop. Okay? So we are going to have the delta P, the pressure drop between the reservoir and the bottom hole, the real one that you are having in your well, and the pressure drop, the drawdown, the reference. The reference is going to be no damage, open hole, smooth condition. Okay? So when you have the bottom hole pressure, the drawdown is exactly the same that the expected, the skin is equal to 0. When the pressure drop is greater than expected, the real is greater than the reference, then you have skin positive. When the pressure drop is below the expected, you have a negative. When you have a positive skin, the reason for this is permeability reduction or real formation damage, or could be also a restricted flow of pseudo damage created by partial perforations. When you have few shots per foot, gravel pads, case, gravel pads, that creates skin damage. When you have below, you can have a stimulation, hydraulic fractures, cyclone steam injection, or you have a acid stimulation in carbonates that create wormholes, or you can have a slanted wells. In the definition, you can see that I am dividing this differential pressure by this QU BO over KH. This value has no dimensions. Okay, what is the advantage of this? The advantage is that the effects are the same regardless of the are proportional equivalent. Okay, here I'm showing two cases. The red line represents the no damage skin equals 0 for both wells. They have different reservoir pressure, different productivity index, but you can see that the proportions remain the same. So when I have a skin about 23, 30, the productivity index and the inflow, you can see the performance is reduced to 25% of the real capacity of the well when the well is in damage. For both cases, you're going to see that the proportion remains the same. When you have a stimulation, the case skin equal -5, is that light blue, you are incrementing the capacity, the potential productivity index of the well. you are not incrementing the reservoir pressure. Look that all of them, they start at the same reservoir pressure here in the in the in this case in the up case, and the in below they start at the same pressure. Okay, but the relationship, the ratios remain the same. So that is the reason of having a dimensionless skin value. So we know that the consequences are going to be very severe when you have a high positive skin, a very good when you have a -4, -5 skin value. Let's talk now about the inflow performance for saturated reservoir when the reservoir pressure is below the bubble point pressure. Um, what happened in this case? In this case, the productivity index is defined at the tangent slope at the pressure, the bottom hole pressure equal to the reservoir pressure, which is highlighted with the dashed line in red. Okay? Remember the productivity index units are barrels per psi. So that's why we is the inverse of the slope. The graph should be pressure, bottom hole pressure in the x-axis and Q in the y-axis. So the slope will be the with the right units. Okay, but this is just a reference number. I'm not saying that is the slope is constant for every point. We are going to see this in the next slide. Why I'm suggesting the pressure should be in the XY, because what is easier to measure, pressure or rate? Pressure device is a manometer or whatever. It's very cheap and easy to install. Something to measure rate is very expensive, especially when you have multi-phase flow. So let's continue with the meaning of the productivity index in the case of multi-phase flow. What is using this example with the productivity index, the tangent at this point is equal to 1. And I am plotting also the tangents at different points. You are going to see how the productivity index or the slope, the tangent change. At the top, the productivity index is 1, but when you are going to the absolute optimum flow, the productivity index is 0.11, which is 11% of the original value. So the tangent is changing. So meaning that when you reduce the pressure at the beginning, you are gaining a lot of rate at the beginning. Reducing 1,000 psi, I got 955 barrels additional. At the end, I only reducing from 1,000 to 0. I got additional 156. So the tangent is changing, but the productivity index is referred to the top, remains equal to 1. So many people think that because it's not a straight line, we cannot talk about productivity index. Yes, you can talk about productivity index, but taking care of the meaning and the definition. Doesn't mean that it's straight line. It means that it's just the slope at the pressure, bottom hole pressure equal to reservoir pressure. When we talk about general IPR core, we have a saturated reservoir, so we have a straight line up to when we get to the bubble point pressure, and then we have this curved line, Vogel type. So the productivity index, we can use this equation, rate equal productivity index and the pressure reservoir minus bottom hole pressure in this straight line, but we cannot use the same equation when the bottom hole pressure is in below the bubble point pressure. When we are calculating the productivity index and we are using a saturated reservoir, then the reservoir is below the bubble, the reservoir pressure below the bubble point. The equation to compute the productivity index is given by this. We cannot use this because this is only valid for single phase liquid. If I use this, I'm going to make underestimations. The color dot explains you the situation. When I'm using the right equation, I'm computing this tangent, and I can use Vogel, I'm going to have the proper inflow curve. If I use the straight line, I'm using this, I'm computing the slope given by the dash point, the red dash point. I mean, that slope, that productivity is smaller than the green, so you're going to have problems. When you have the saturated reservoir and you're using the bubble point, productivity index is very simple when you are in the straight line, using the standard equation that everybody thinks applies for the whole range. But when you are below the bubble point, you are going to use another equation for this. So want to clarify this typical mistake in the inflow, let's talk about the outflow of the demand curve. And we are going to talk about the outflow for reducer wells with the node at the bottom hole. So when we have multi-phase flow, we have patterns, well know this. And pattern means that the friction factors and the liquid average liquid density is going to change. It's not going to, there is no a single equation that you can use for all of them. Usually when people trying to match well in using whatever software is in the market, they always try to match the bottom hole pressure without doing a previous match of the PVT correlation. When you are using the wrong PVT correlation, then for a given pressure, if you are using, for example, the PVT at the right in the left side, the prediction of liquid is 90% for this temperature. Meanwhile, for the other PVT, you have about 50%. That will change a lot the density. And if you have the density wrong, you're going to have the a big error in the pressure drop computation. Next common question if I can use Thomson and Ross or Hydron and Brown, whatever, with condensates, because people think it can be only used in black oil. When you see inside the multi-phase flow computation, you are going to see that inside you never ask about is a condensate, whatever. You are going to see how much is liquid, how much is gas. You are going to see the PVT property. As soon as your PVT properties are properly set for your oil, even condensate, whatever, it's going to work, and it's not a problem of the multi-phase flow correlation. Especially take care with the solution gas. Just to show you how it changed. For the API, light oil, they have higher bubble point pressures and higher solution gas. Heavy oil, they have lower bubble point pressure and lower solution gas. You have the original correlation, PVT correlation, or you can use equation of the state if you have the composition. And then you have to do a fine tuning for the original correlation to your data. And then once you have this, you know that the quantity of the solution gas is going to be okay, and the prediction is going to improve a lot without still doing the tuning of the friction factors and hold up in the pressure drop correlation. Typical question, wrong typical question. What is the flow pattern in the tube? This is a proper question because the flow pattern can changes along the tube. So the proper unusual question, nobody asked me this, what and where are the patterns taking place in the tubing? Clearly, the tubing cannot be analyzed as a one single piece because there is no a single equation for this. You have to divide the two in segments and then making the computation. Usually we start at the wellhead because measuring the wellhead pressure is very simple and commonly performed in the field. What is the procedure that we use to understand how the outflow is computed and what does represent? So we start with the wellhead pressure. We divide this in segments, imaginary segments, and then from the wellhead, I estimate I have the intake pressure, which is the wellhead, and I can compute the output pressure of that segment. For next segment, the input will be the output of the segment 2, input will be segment 1 output, and so on to reach the bottom hole. When we perform the corresponding computation, you are going to see that the gradient changes. The lighted gradient is at the top because you have more gas free at the top than in the bottom. We can compute how much liquid you have at the top, and you can see that it's changing, and you can see the flow patterns predicted at different locations. Even single phase liquid is at the bottom, very bottom. The last 200 feet are liquid in this case. We can see how the solution gas at the very bottom, all the gas is in solution. We can see the properties of the fluids, and they are changing. I start with the intake pressure, I compute the output pressure for that segment, then I use this output for this input and so on to reach the bottom hole point pressure, which is the pressure for this given rate, GR, water, and tubing diameter. I can perform this previous computation, this previous table, iterative procedure for different rates. So for 10,000 barrels, I have the violet profile, and the final pressure is this value. And I can repeat for different rates. Then plotting, knowing the rate and the final pressure, I can plot the bottom hole fluid pressure versus the rate. And that is going to be the outflow core. Pay attention that the outflow core has an initial part, multi-phase flow, that the pressure is higher for lower rates and then decreases until reaching the minimum and then starting again. The previous area, the first area is called the liquid loading or gravity domain area, and the second area is called the friction zone, or you can see that increase with the rate as expected. This is important because it's one of the criteria to identify well stability. When the well intersection and inflow and outflow, the slope of the outflow, the tangent, which is shown here with the dashed line, is positive, we have this is a steady state and a stable condition. This is unstable condition. It's a steady state, but it's unstable. What does mean? This means that we are, why is this unstable? This is unstable because the well is loading liquid at the bottom. So sooner or later, it's not going to maintain the same condition. While there is no liquid loading, there is no liquid accumulated at the bottom, everything is dragged to the surface. So that is a stable condition. To understand this, consider this to understand this. These two cases, this is a ball placed at the top of dome. That is a stable, this is a steady state condition, but it's an unstable equilibrium. What does mean? If I just push the ball a little bit, whatever direction, it's going to start going in that direction, and there's nothing that that tries to put it in the original place. Meanwhile, when you are at the bottom of the bowl, if I push to the right, then the gravity component is going to push to the left, and vice versa. So there is something that tries to put the system again in the equilibrium position. In the case of the previous plane, when I just to show you the same, when the when I try to reduce the rate, the outflow requires less pressure and the inflow requires more pressure. So they oppose each other. The same. If I try to increase the rate, the inflow requires less pressure, but the outflow requires more pressure. When you are here, it's not the same. If I try to reduce the rate, the inflow requires less pressure and the outflow too. If I want to increase the rate, the inflow requires less pressure and the outflow too. So it's on an unstable equilibrium. When I have artificial lift, what is going on? When I know at the bottom hole, then what happens with gas lift, you are adding gas into the well, and then the procedure I previously explained, you have to take care of adding the gas, the injected gas to the total gas in the multi-phase flow pressure computation. You can see that, again, I can use the rate and the final bottom hole pressure and plot the outflow. This outflow curve will include the gas lift effect. When I have pumping methods, the difference is going to be that the pump creates a jump in the profile. Again, if the node at the bottom hole, the inflow is going to, the outflow curve is going to include the pump performance in the result. So the pump just increase pressure. You can see here the jump, and depending on the pump, the pressure increase in the pump depends on the rate. So when having a pump, we always can do nodal analysis, knowing that you have to include the pump performance in the pressure drop computations. Let's talk about injection wells. In injection wells, it's very important because never mentioned in the non-analysis courses. People think that I have to make corrections to the inflow and the outflow. No, you don't have to make a change in the inflow. You have to define properly what is the inflow and what's the outflow. Being the node at the bottom hole, the inflow is everything upstream. So the inflow is going to be the pump, flow lines, tubing, depth, and we are injecting just water or gas. It's not usually it's not multi-phase flow in the tubing. So my inflow is going to be the production system, and the outflow means everything downstream. Downstream is going to be everything here. So the outflow is going to be the reservoir. So everything changes, but the idea remains the same. We are dividing the system into subsystems and changing the roles because of the direction of the fluid. Also, you have to pay attention that the injection well, the bottom hole fluid pressure is greater than the reservoir pressure. Production wells, the bottom hole fluid pressure is lower than the reservoir pressure. And here we can see that this red line, that is an outflow straight line, is the reservoir, and the inflow is the tubing plus the pump plus the column. So the depth and the tubing is, and the diameter of tubing is included in this case. We can use the nodal analysis to see different scenarios, to see if we can have our target Suppose that we need to inject this target in an injection well, 10,000 barrels of water, whatever. So every intersection point below, we having a lower target, it does not satisfy our requirements. So we are going to pay attention to the intersection points that having higher rates than the target. So, and then we can see if we can reach that target. Having an additional constraint that we have to take into account the fracture pressure. If the intersection point is above, is in this case, this intersection is in the fracture pressure, we cannot use, in this case, we cannot, this scenario is going to create a fraction, it's not possible. But this intersection, these three intersections points, 1, 2, 3, 4, 4, they are feasible. And then we need to know what are the reservoir pressures and if our formation is damaged or not damaged. Well, that's all for today. Thanks for your time. If you have a question, please feel free to do it.
Thank you very much, Sergio.
You're very welcome.
Okay. So I think that we finish for today, and next time we will have probably another presentation with you. So thank you again for your time, and see you then.
Okay.
Bye.
Have a nice day. Bye.
You too. Bye.